Hello, everyone. My name is Erin Winick Anthony, aka at Erin Winick on social media, and welcome back to Eureka Hour. We have a pretty awesome guest here today to talk about everything from lasers to space. Her name is Meriame Berboucha, aka Girl in a Physics World on social media. And when I was working over in London right after I graduated, I got to meet her, and I'm so excited that you all get to meet her today too. She is currently studying and getting her PhD in plasma physics and is an expert in all things lasers. So please join me in welcoming Meriame.
Hello. Thank you for having me, Erin. I'm so excited. And hello, everyone. My name is Meriame, and I'm a laser plasma physicist. So thank you for having me.
Awesome. Yes, thank you so much for being here. So I gave you that little intro. Would you mind giving a bit more of an intro of what your background is and what is a laser physicist?
Yeah, I get that question all the time. Yes, I have a background I have a physics degree from Imperial College in London. So I'm British, but also Algerian. So in case you don't know, Algeria is the biggest country in Africa, but I was born in London and then went to Imperial College for my degree in physics. And then from that degree, I then did a master's in research in photonics. So if you know what electronics is, that's the kind of movement of electrons, so the study of the movement of electrons, but photonics is the study of the movement of photons, so like packets of light. So I did that for my master's, and then now I'm still in school, haven't had a job yet, and I'm doing a PhD in laser plasma physics. But yeah, what is a laser physicist? Well, I basically work with some of the most powerful lasers in the world to learn more about the universe around us. And more specifically, I try and recreate the conditions found in space to then help us with something called fusion. And so we'll delve into that later, but essentially we're trying to get clean energy on Earth and harness the power of the sun on Earth. And that sounds terrifying, but it's totally safe and it's totally fine. And it would save us from all our energy problems. But I am now in my third year of my PhD, and I've got about a year and a half left, and then I'll be Dr. Berboucha. So
I'm going to be so excited for you. What actually is a laser? I think a lot of us have seen lasers in like sci-fi and things like that, but when you're actually working with them, what does it mean that you're working with a laser?
All right, let's start off with, so everyone has like a torch on their phone. So this light has loads of different colors and it goes in all different directions. But a laser, if you've ever used a laser pointer before, goes in one direction and is of one color. And so that's kind of like the brief description of the difference between like lights from your lights in your home right now, or what you're watching on us on the TV or your phone. They all have loads of different colors and they go in different directions. But lasers, like laser pointers, have one color, one wavelength, and they go in one direction. But laser pointers can fit in your hand. The lasers I work with are rooms. The biggest laser in the world is at the National Ignition Facility in Livermore in California, and it's 10 stories high and the size of 3 soccer fields. So it's huge. And these things you can walk through. Some people use bikes to get around them because they're such big rooms. And the reason why you need big rooms like that is because you start off with what the actual laser starts off with, which is like 2 mirrors, and you have something called a lasing medium. So a lasing medium is basically something that if you excite it, it will start to produce light, and then you can amplify that. And these amplification stages need loads of room because you need to amplify that light to many, many times stronger than what you start off with.
So, okay, we got what a laser is. Now I don't know, why were you interested in starting to study lasers? It sounds like you've kind of been honing in on this as you've, gone through your education.
So when I was about 10, I wanted to be an artist, and then that changed because I was kind of introduced to what an artist's life was, and it seemed kind of unpredictable. And when I was 10, I was like, I think I might change my mind. And then I got into long distance running, and then the same thing happened. I was just like, I don't see this as a long-term option for me, at least, because I was so interested in maths and science. And then I got introduced to physics at school, and I decided to realize, like, there are so many questions we don't know the answer to, and that was exciting to me. And so I changed my application for university from medical school to physics, because I just can't see people suffer. I have a big heart and I find it really hard to see other people suffer, but I wanted to help somehow. And then I discovered medical physics. And so there was a lab in Oxford that did a little medical physics like class, and I decided that I liked the combination between medicine, maths, and physics. And then that's how I got interested in physics in general. And then I applied to Imperial College, got in, thankfully. And then I did an internship in my first year of my undergrad. And I was invited to a laser lab, and I was like, that's it. I love this place, because I saw people put on these laser goggles and they're like tinkering with different optics and like all these colors, and it just looked like a sci-fi movie, and I wanted to be a part of it. It just looked so fun, and I was like, how do I do that? How did you get here? And I want to do the same thing. And so that's how I got interested, is purely the aesthetic, I think, at the beginning of the lab. And then after that, I really got interested in the theory behind it. But yeah, it just looked so fun, and I wanted to get involved.
We have to talk about then what you wear in a laser physics lab. So you've talked a little bit about not wanting to look at them. So I'm guessing you've got some eye protection.
Yeah, exactly like that. So these are laser goggles. And exactly what you said, Erin, we do not want any beams going through our eyes and destroying them, and you will become blind. So like I said, you can get many joules and watts of power that would just be going through your skin or your eyes. And the lasers I work with tend to damage our eyes the most. And so those are really important to protect ourselves and our eyesight. Our eyesight is so special to us, so we don't want to lose it. So on the screen now, you can see that I've got my laser goggles on and a lab coat. So there's kind of two things we have to worry about, is dust on any of our optics. So that means lenses, mirrors, because the laser has so much power that you can kind of have these hot spots that if dust collects on them can damage the optics, whether that's mirrors exactly like this. And so you can see there's like some mirrors in front of me there, and we want to keep them as clean as possible. So I put my hair, I tie it, and then I put it in a hairnet. And you wear a mask for the same reason. You don't want your hair or dust or even just like droplets from when you're speaking onto any of the optics, because we're dealing with such high power lasers. And so we don't want to damage anything. And then the lasers are off in this picture, so don't worry, my eyes are protected. But on top of that, I would wear those laser goggles, and we want to protect our eyes. But another thing that we have to worry about is the color of the laser that we're looking at. So I did say before that lasers have one single color, and you have to wear goggles that protect against that color. And so the orange tones that I was using before in the laser goggles kind of protect us from infrared lasers. And so when you put them on, they are kind of like sunglasses in the sense of like they block certain wavelengths, certain colors of light, but more importantly, they suppress all of that energy so that it doesn't go into my eye and I'm protected. But in general, we are always careful. So we put things like beam blocks. So we're blocking the laser beam. We always know where the laser beam is going, but this is just in case. And that's why we don't wear any jewelry. So these rings I have to take off when I go in, even my earrings. And I love jewelry and I love fashion. So every time I'm like, oh no. But I have to be safe because these are reflective. And if the laser is to reflect off of it, it might go into my eye. And the worst thing is watches. Watches are super reflective, and you just pointing your wrist in different directions can direct the beam into somebody else's eyes or your own. And so we have to remove all of our jewelry. And I wear gloves for the same reason. We don't want our dirty, oily hands on the optics either, but also they're less reflective too, and so they protect us. So those are kind of the things that we wear when we're in the laser lab to protect our eyes, but also the lasers that we're working with and the mirrors and the lenses, so they don't break also.
What are you studying with these lasers that you have specifically chosen? What is your current project that you're working on? Oh, actually, before we get into that, we have a quick question. Yes. Do you have special shoes?
I do. And so let's see if I've got a picture of them that I can quickly show. But I wear Crocs. I don't know if you've ever worn them, they're really comfortable, but we're always in the lab for long hours. And so they look like this. I don't know if you can see the Crocs, but they're yellow, so they match the lab. So my lab is yellow. And the reason why we wear Crocs is for the same dirt reason as before. And so any shoes from the outside have dirt from the outside, and we don't want that in the air moving around. And so we have certain lab shoes. So as soon as I walk into the lab, there's loads of laser safety signs around me telling me that the laser is on or off, what wavelength, so color of light is going in the lab. And then I put my hairnet on, my goggles, my face mask, my lab coat, and then those shoes. And so that kind of gets rid of all the dirt really from the outside. And then I'm covered head to toe, and then I can walk into the laser lab. So that was a great question.
A very important question here.
I have Jigglypuff, Wonder Woman, and Captain Marvel on my Crocs.
Premium selection there. I love that. I will say I was expecting the Crocs to be pink, so I was surprised after you said that they were yellow.
Yeah,
but you got some Jigglypuff on there, so a little bit. So yeah, that's great. What are you doing in this lab? What are you studying?
All right, so we're going to start at the beginning. So I do use the high power laser in a lab called the Matter in Extreme Conditions. And that's exactly what I do, is I probe matter in extreme conditions. And these tend to mean conditions found in space. So astrophysical scenarios, like we can also look at the interior of the sun, interior of planets, fusion reactions, things like that we can all do with lasers. And the reason is lasers have lots of high energy in a short amount of time. And so you can have lots of watts going through in such a small amount of time, and that's a really intense pulse. So what I do is I use that laser, I focus it onto a gas, and then, funnily enough, so this is where the laser plasma comes into my work, is I have a laser and I have a gas, and when you heat up a gas, it turns into the fourth state of matter, which is called a plasma. And that's when atoms no longer exist because it's so high energy that atoms can't hold themselves together and they lose their electrons. And so now you get a soup of ions and electrons floating around. And so you have electromagnetic fields going around. So when I have the laser going in, you produce this plasma, and the sun is made of a plasma. So if anyone tells you that the sun is a hot gas, now you can tell them, I know it is a plasma actually. And so we have a laser onto a gas, turn it into a plasma, and now with the laser, you can influence charged particles, so electrons, and cause them to wiggle in the laser beam itself. And then when you have charged particles that wiggle, you can produce X-rays. And so these X-rays are pulsed just like the laser pulse that comes in. And so now I have an X-ray flash camera. And so I use a high power laser to basically focus it onto a plasma and produce an X-ray flash camera. Now with this X-ray flash camera, X-rays have a short wavelength. And tell me when to stop, because I know this is a lot of information. But X-rays have a really short wavelength. And the shorter the wavelength, the smaller you can see. So with X-rays, you can look at the atomic level, so individual atoms of something moving. And what I look at is what is inside planets like Neptune and Uranus. And this matter is called warm, dense matter. Essentially what that is in between a solid and a plasma. So plasma is like a really hot gas. And then we all know solids, and in between that is kind of like you have the solid structure, but your electrons are warm. And so they're floating around, but you're not quite warm enough to be a plasma. And that exists inside planets like Uranus and Neptune. And researchers in general actually don't know much about warm, dense matter. But warm dense matter can also be added to fusion reactions, because when we use high power lasers to make fusion reactions, so what powers our sun, warm dense matter is made in those reactions. So I do experiments to learn more about warm dense matter to then help fusion scientists learn more about their fusion reactions made by lasers. And so we actually don't have good models for warm dense matter. We're doing experiments, so we're learning more about warm dense matter, but we actually don't have good models to tell us how they work and how they function in pressures and temperatures and densities that we know and understand in space.
What are you most excited about in your research right now?
That is a great question. I think for me, being able to contribute something that other researchers can use. And so the biggest thing, and I don't know if I can do it on my own, I think that's why science is a collaboration. It is global. We want people from all over the world, brains from all over. We need all those brains together to be able to find new stuff and discover things. But for me, it's like knowing that any research I do right now is going to add to this warm, dense matter, like theory and just general explanation of what the matter is so exciting for me, knowing that any experiment I do is contributing something to those theories. And so I find that really exciting. But day to day, so that's like the grand goal of my research.
Sure.
But day to day, it's honestly just being in the lab. Like I love putting on all of my gear, and working with lasers is so fun for me. I work in a big vacuum chamber that I could like lie in. It's like 2 meters long. And so I could crawl inside, and I crawl inside to work with my mirrors and different optics in there. And so I find that really fun. I like working with big machines. But my lab is also connected to the longest linear particle accelerator in the world. So if any of you know what CERN is, it's like a circular particle accelerator, but SLAC, National Accelerator Laboratory in California, is a linear particle accelerator, and it's like 2 miles long, and we accelerate electrons down the linear particle accelerator to almost the speed of light, and then we wiggle them with the magnets. And the same way that I produce X-rays with my little gas and a laser, you're doing the same thing, but now you're wiggling electrons with magnets instead of a laser beam. And you can produce X-rays that way too. So I work at like the only place really in the world that does stuff like that. So that's really exciting.
What a cool place to work.
Knowing that I get to go to that every day is like so exciting. And I moved from the UK to the US to work with bigger machines, and there's more funding in the US. And so those were the things that drew me to coming to the US. I'm so glad I got accepted because it's been so fun. So that's the day-to-day like joys of my job is.
And now this is a perfect pivot to one of the other things I know we wanted to talk about today. Have you been to a Lawrence Livermore National Laboratory and seen the lasers that they used in their fusion breakthrough? And maybe also start out by, could you describe what that fusion breakthrough was?
Exactly. So if anyone knows, LLNL is Lawrence Livermore National Lab. So that's in California. And the biggest laser in the world is there that I was talking about. It's 192 laser beams, all focused onto a little gold pellet. Inside that is hydrogen fuel. And all this laser energy from those 192 beams are going into this into this fuel, and we're trying to get fusion to happen. And so that was a great question, because we are going to talk about that. And so back in December 5th, a huge fusion breakthrough happened at NIF, so the National Ignition Facility. So this is the largest laser in the world. And essentially what they were doing is recreating this fusion reaction, so what powers our sun, and their laser energy was about 2.05 megajoules, so million joules, onto their target. Now, to have fusion happen, you need more energy out than you put in. And in general, in the sun, what happens is you have lighter atoms, so hydrogen atoms, with like a few neutrons added here and there, so deuterium and protons smashing into each other, and tritium. And then after, you get heavier atoms, so you can get forms of helium occurring afterwards, and then an outburst of energy. That outburst of energy, if we allow that to happen on Earth, is what would give us like energy to power our homes and the national grid and all things like that. So we're trying to get that to work, because it would be like a clean way of getting endless energy. And so the big breakthrough was that with 2 million joules of laser energy onto this gold pellet with the hydrogen fuel, we actually got 3 million joules out. So 1 million joules difference of output.
Wow.
And this is something that we call ignition. So maybe if you saw on the news, the word ignition was floating about, but that is where you have a fusion reaction that is self-sustaining, which means that when the fuel is heated up, this heats up more rapidly than it cools down. And so that's what we're aiming for. But obviously this happens in like a really short time, and we need to continuously power this reaction to then keep getting all this energy out. So those lasers need to continuously fire. And the problem with the fusion breakthrough, although this is really good, it actually takes about 300 megajoules of electricity to even power the laser in the first place. And so we still have a bit of a way to go before it becomes efficient enough for us to have commercial fusion. But the fact that we put 2 million joules in and got 3 million joules out is a huge thing, and we've never been able to do that before, ever. So that was a Christmas present of last year, and the biggest breakthrough, in at least in my field, for a very long time.
Yeah, we got another question here. What is the most mind-blowing fact about lasers? Yeah.
All right, I came prepared. Okay, so at least I find this fascinating. I don't know if everyone else will, but I don't know if you know this, but you can levitate objects with lasers. So if everyone remembers the E=mc² equation that Einstein postulated, and it's everywhere, like every time you think of physics, that's probably the first equation you think of. So energy and mass are interchangeable. Now, when you have light, so a photon, like a packet of light, it actually has no mass, but it has energy. So technically, energy and mass are interchangeable. And so you can think of photons, like light, as little balls. And so these little balls can also carry momentum. And momentum means you can push things. And so actually with a laser, if you focus it onto a water droplet or other nanoparticles, you can make them levitate with lasers. And so I think that's really cool. But you can also like pick up atoms with like optical tweezers is what we call them. So I remember being in a laser lab at Imperial College and seeing like a droplet of water being levitated by a laser, and I was like, this is insane. I would see it with my eyes, and it was crazy. And so I think that's a cool thing about lasers, because like it was like a small little lab in my university, and to know that was happening in the basement underneath where I was taking lectures, I thought that was really cool.
Do lasers actually exist that cut us in half, like in Star Wars?
Okay, they won't cut all your flesh that hard, but they could definitely hurt you. So the reason why they can't cut completely your whole body is there's something called a penetration depth. So your light can only go so far into an object. So I don't know if you know this, but you can cut things with lasers. So we have like loads of like laser welding, you can cut fabric. And so those fabrics or metals can only be a certain thickness that the laser can penetrate through to actually cut them. So the human body is a bit bigger than that, but I'm sure it could cut your nail. But it could definitely give you cuts on your body, but it won't split you in half. I'm sorry to get that out of movies.
I mean, maybe that's good news. I don't know. It depends on which side you're on, I guess. But yeah, I think obviously people think lightsabers, when they think lasers, and I think, correct me if I'm wrong, but lasers is also an issue with like creating an end to them like that. Like there would just be like a beam that has like a defined end. Is that correct?
Yeah, you can never do that with lasers. They're going to keep going. Yeah.
Okay. So it has a penetration depth, but if it was unblocked, it would just keep flying off into the distance. Okay.
Exactly.
What is the path to getting where you are if someone else also has that passion for that?
Definitely start with a physics degree. You'll definitely need that. And at most universities now, because lasers are so kind of easily made, at least in the like university setting, most universities have lasers. Just ask to even visit. And so that's how I started, is there was a lab tour and I got to visit a laser lab, and then that's how I fell in love with the first laser lab that I went into. And so those are things you have to do, but you do have to put yourself out there. And I think that was something I found hard at the beginning, is like asking for things. Because I think when I was younger, like teachers, I don't know, like tell you to do homework and they tell you to do things, but then once you reach university, you kind of have to put some work or effort into what do you want and try and get it. And I think that's always been my motto, is like, nobody's going to do it for you. You got to go ask and go get it. And so I, in my first year of my university, got to do a placement, so a research placement in a laser lab. And then I got to visit other local facilities in the UK. That was really exciting. And I think it's just, you need to network as well. And sometimes it's the people you meet that can help you get to where you want to be. But yeah, physics degree, and then try and get some experience. So there could be listings for internships in local labs at universities. Even if it's not your own university, you can check other university websites and get experience in a lab. And whether it's a laser lab or another lab, you might, enjoy another lab even more than a laser lab. But for me, I tried a few labs. I even tried doing medical placements, and I realized like laser labs were cooler for me. So I decided to do that instead. But yeah, like look out for listings for lab tours, internships, whatever you can find, and just apply. Even if you get a rejection, one of them will come back positive. And even if it's just shadowing somebody for one day, it can make a difference. And so that's kind of one of the things I would say is look out for opportunities and ask when you can.
If you're watching this, you must have really liked the video. Make sure you follow and subscribe, and check out these other videos that are even better. No, really. I've seen this one over 100 times.